Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Three talks about services, so from our foundation to moving up one layer. And it's my pleasure to introduce for our first post-launch talk as Joe Hoshman is going to be talking about second-generation sensor querying languages, with the first presumably is TinyDB and its follow-on. So now we'll hear what's next.
Thanks, and thanks for scheduling me right after lunch so I can stay awake. This is my sleepy time. I hope I will keep the rest of you awake. I'll do my best. There's joint work with a bunch of people, students, former students, colleagues. Oh my gosh, I left Mike Franklin off the title slide. Well, he's in there, absolutely. So yeah, colleagues, even the ones I respect so much that they're like air, I forget about them. I need them so much I forget about them. Wow. So it's quite a cast of people, and I don't mean to take credit for much of it. I'm just describing it. So I want to spend a little time looking back at the first generation of systems we built at Berkeley and Intel Berkeley, TinyDB and Task. Talk a bit about those. And then to talk about, and this is the work that the authors on the screen, the first screen, can take credit for. It's two different approaches we've taken towards incorporating statistical models into querying over the last 2 years. Sketch out a sort of a software agenda we're now working on called the Sensor Data Library, SDLib. And I have an interesting application that we're thinking about pursuing that I wanted to use at the end just kind of for fun, but also I hope we'll be using a lot of the ideas from before this for that application. Okay, so looking back a few years, quite a while back in the 90s even, there was people at Cornell were talking about device databases and subsequently sensor databases. And I think in Deborah's historical viewpoints, I think that Cornell, Praveen Seshadri at Cornell had databases on Java rings in like 98. So that stuff goes back too, and I wouldn't take credit for that myself either. They were very early. And there's this idea that somehow these devices or the sensor network could be viewed usefully, metaphorically, as a database, and that might be a useful metaphor for dealing with large quantities of data-producing devices. And we went off and took a cut at this with the TinyDB project at Berkeley. And sort of looking back, and this is the slide where I will, in my best Midwestern way, I'll try to praise myself. I feel like we did some good things. Part of it was timing, I think. We did this at a time where I think the impact was high, and it opened a lot of eyes to, I think, a community of people who hadn't been taking sensor nets as seriously until this came along. Obviously, we were raising the abstraction level for sensor nets with a very familiar metaphor, one you could describe to people who worked in IT, people who worked in enterprise software, and so on, was to say, you have lots of processes that are ongoing. Wouldn't you like to query them the way you query your database that stores the results of those processes? And they said, of course. And so just that alone, sort of being able to have that conversation with people, I think, and being able to demonstrate that kind of a system was very useful at the time. Another thing that I'm pleased about looking back at the work is that it really was one of the first holistic applications in the usual software sense of applications. It was a piece of software that did a bunch of stuff that was not just single purpose and not very focused, but it sort of was a broad, useful application. I think we're the first to really get something off the ground and running like that in this context. And in doing so, we touched on, and I won't say we did a great job of, but we definitely touched on a whole family of issues that I've seen addressed again and again since then in ever better ways. So we were one of the first systems that was field configurable. You could send it commands while it was live, and it would opportunistically disseminate those commands. So when a new node came on, you turn on a new node, it would hear about that command, and it would go off and join the network and do it. So it's a much more flexible installation kind of than any of the systems before it had been. And in doing that, we did it in a very simple way, but it worked quite nicely, and people have followed on from there. It was an interactive system, particularly when Task came along and they built field tools around TinyDB. So you could walk around with your little Palm device, see what the network was doing. You could use the same interface to query the status of the system as you did to query the data. So you could say, what's going on in my network? What's the topology? That was just another query in our system. So this kind of notion of interactivity, of configuration tools and field tools and all that, we had a first cut at that in the middle of this, simply because we were trying to build something useful. It was an example of a sensing environment where there was a way to talk about pulling data and a way to talk about registering triggers that would push data. And we thought about both of those things in a single architecture. And again, I'm not claiming we did the most detailed job, but we did both of those things at once. We had an abstraction layer where we schematized hardware and software sensors. So if you wanted to find out something about the node, it didn't matter so much from the application perspective, whether it was a device or whether it was a name or some other attribute or a function that you had coded into the system. And I think, sort of the deepest contribution of TinyDB was the idea of taxonomizing the interactions between the logic for handling the data and the communication layer for getting the data through the network and dealing with it. So things like identifying that certain functions would be insensitive to duplicates being transmitted in the network, and you shouldn't think about delivering a packet. You should think about getting a source of data out somewhere, somehow. And when that is possible for a function, then you can use redundant transport in a variety of ways. And so being able to call this out, go try to find functions that are duplicate insensitive, led to a whole bunch of creative work, including by people in this room, on things like using sketches to get counts. Another one was if you have a monotonic function, then you can do Snoopy suppression, where if you hear somebody say something, say, lower than what you're going to say, then you don't have to say anything at all. Right? So the idea that there are functions that are monotonic, and if you can be aware that such a function is running, you can avoid communicating by listening. So these kinds of identify something about your computation and then change your networking protocol as a result, I think were the deepest contributions. And getting that into an API where you could register new functions opaquely and say, you don't have to know what this is, you just have to know that it's duplicate, insensitive, and monotonic. Go do the tricks you do for those sorts of things. I think this was the thing that we're most proud of, and that at least at an intellectual level, was the biggest contribution. The other thing that I think was useful at the time we did this was we were kind of the customers of the platform, or at least of the TinyOS Berkeley platform. So we drove the agenda, I think. We were pushing that platform. We were greedy about having code space and memory space and things like that. When things were bad in the radio stack, we found it quite often before other people did. I think Sam Madden pushed back on the TinyOS group a lot more at that time than other people. And then in a similar way, more broadly for the community, we did a first shot at a whole bunch of things. And that opened us up as a really nice, convenient target for everyone to shoot at. And so there are many papers subsequently saying, oh, TinyDB did such a stupid job of X, and it did such a stupid job of Y. And that was great, because then people had problems to work on that came out of just somebody doing something horizontal. And so I think, in those terms, the timing of the project was nice, and the sort of the idea of doing something broad rather than something deep. I will say that this was kind of, for me, it was the first in a series of research agendas that I'm pursuing now that I call Declarative Networks, which is coming back and revisiting networking from the transport layer through topology specification and routing as a query processing problem. And we're now doing this also at internet scales. We've had a couple papers this year I'll refer you to, so that's sort of an aside. But this was, for me, also very inspirational work for my current agenda. So there's some systems lessons, sort of typical ones that came out of this. One is, you should throw away the first version of your system, and it's certainly time for us to do it with TinyDB. It's a very monolithic design, and as a result, people haven't reused a lot of the things we did inside of it. So even at Berkeley, there's a whole bunch of tools that David Culler's group has subsequently built, which, cynically, I'm like, wow, TinyDB could do this, TinyDB could do that, but TinyDB also would use up all of your code space. And it's hard to support, and so on. So we didn't do a good job componentizing because we didn't know what we were doing when we started. We just started adding features to make the darn thing make sense. The only piece I think that's going to survive is just the schema layer. In fact, Tiny Schema is something that can be reused. The thing is big. Getting it to run on a Telos mote is currently a problem for us because the code size on those is smaller than on the Micas. So that's always been a problem, and it's a real problem now. Another problem that happens with academic code is either you start a company or you have to get new graduate students onto the code base. And currently this code base has 0 graduate students. It has 1 MIT professor and 1 guy at a startup who no longer does research and 1 professor who didn't write much of it to begin with. So that's the programming team of me, Sam Madden, and Wei Hong. None of us has time to maintain TinyDB. Whether startup companies or large companies will be pursuing these software bases, I can't comment. I don't know. But this is a problem. The other thing, and I think this is something that Chris referred to earlier, I'm going to agree with Chris more than I expected to, is that we did too much too soon in a lot of ways. So we had a lot of things that we thought were interesting that were never exercised by the early adopters. Things like in-network aggregation, which we made a lot of, and a lot of our optimizations are tuned for, were things that people didn't want. And the base case that people wanted was data collection. So this is the query we would typically see from users. Select star from sensors every 5 minutes. Just get me the data at this rate. And you'd go back to them and you'd say, but I can get you, more interesting data more often for the same energy budget. They'd say, no, we want all the data. You say, well, what do you mean you want all the data? They said, we want all the data. Don't, coalesce it in any way. And we'd say, but I can get it for you every 1 minute or every 30 seconds at a coarser grain. They say, no. We need all the data. So for them, spatial compression was bad, sort of, and temporal compression was better or something. They were unhappy if we would throw away a reading once it was taken. So fine. Those are all interesting lessons. Some positive things, though, again, is that the high-level query interface, even when used very simply, was very attractive to people. They didn't think about the nodes in the network. They didn't think about any of the details. They just thought about what data they wanted. The problem being that SensorNet as a database lived up to the acronym we used to get teased about, that this was SAD, SAD. This is the wrong abstraction. And I think Carlos Gestrin was the one who finally beat us over the head with this. That you're not enumerating a fixed set of data. You're acquiring data from an environment. And just because you've acquired it doesn't mean it's truth. And in acquiring it, you're probably introducing all kinds of biases that you wouldn't expect in a database of employees. Okay, so it's incomplete data typically. It's incomplete in time for sure. It's probably incomplete even amongst the sensors because you'll drop data. It's certainly not an unbiased sample of some spatiotemporal phenomenon. And so even if you want to interpret the data as a sample, you really can't. Whatever data we lose, we don't predict or interpolate in any interesting way. We just say, here are the readings we got, and maybe we averaged them for you, which makes it even more confusing. And basically, I think all but the most sophisticated people would misinterpret the results that would come out of TinyDB. So you'd say, the average temperature, oh yes, I understand. I think that means the average temperature in space, but it doesn't. It's the average of a set of readings that we successfully routed through the network. So there's a problem with the metaphor sort of in terms of its correctness. And then there was a problem in terms of efficiency, which is we were working so hard to get all the readings. So this is sort of the flip side of it. When in some spatial region, all the readings were probably the same anyway. Why were we working so hard to get all those temperatures out of the hot part of the room at the same time? And this is where I start to disagree with Deborah and Chris that it doesn't make sense to just route all the data out because a lot of the data is redundant. And you can do a lot of things inside the network to detect that the data is redundant, or contrarily, which was the answer given earlier, to detect that there is a reading here that makes no sense with respect to the readings around it. And if you ship all that out first and then think about it, you're doing more work than you need to. There is significant spatiotemporal correlation in the real world. You can take advantage of that in lots of ways. So very much as a result of Carlos Gestrin spending a year with us at Intel, we shifted to a more statistical model, and we only very slightly modified the metaphor. So we basically could keep the language, we can keep the metaphor more or less, but rather than the SAD, we've got the WAD, which is the world as a database. It's such a big database that you can't have it. So you should think about what from it you would like to acquire. And a term that I think Mike Franklin and Sam Madden coined, acquisitional query processing, very much is the theme of this. Coupled with using statistical models so that you can talk about what would be the value of acquiring a particular piece of information, which is kind of a classic statistical problem. But in the midst of this, retain that sort of enterprise-style declarative view of saying what you want, not how to get it. All you really need to do is add some confidence intervals to SQL to say, get me the average plus or minus 1 degree with 95% confidence. And this time, can you please make it the average of the temperatures instead of the average of the readings? Okay. And hopefully, in doing so, we can provide not only better answers, but also more efficient answers. Yeah. Okay. So we've done two completely different approaches to this, which we have not synthesized at all, which is part of the theme of the future work. So the first was called BBQ. And BBQ is a system that does model-driven data acquisition. So, we were trying to come up with a name for the project, and we all decided we had this branding with Tiny at Berkeley. And so we had to have a Tiny something. We had done TinyOS, TinyDB. So, we were going to do Tiny what? Tiny model, Tiny model. And so I suggested, well, if it's a tiny model, we should call it Barbie. And Carlos didn't like that at all. For some reason, Carlos was fixated on the idea that we should call it Q. And I didn't understand what he was talking about. And he said, Q, it's the guy from James Bond who makes all the cool gadgets. It also could stand for query. And so I think it was Wei Hong said, why don't we just put them together and be barbecue? And that's what we ended up with. So the name is very hard to explain. But it's not as bad as Ken, which is the next system, which is, of course, Barbie's little friend. That one's really hard to explain. But it's actually cleverer because Ken also means to know, which is fun. Anyway, this is all an aside. So here's a problem with TinyDB. This is a slide stolen from Carlos from our VLDB talk. Here's how TinyDB works. A SQL-like query comes in. It's distributed, usually flood-wise, into the network. Data is routed up, usually tree-wise, back. And answers are provided, to the user at every epoch, every time step. So the query goes in once, and every time step, data routes up some tree. The trees adapt, but routes up some tree to the base station. And if you have a new query, well, guess what? You have to do the whole thing over again. You have to redisseminate the query, start over, start gathering new data. So nothing is taken advantage of in terms of sort of caching, if you like, of learning things over time. So every node must receive every query, which is a bummer. A lot of times, as we said, we don't need data from every node because of all this spatial correlation. And then in terms of the actual collection that happens, we had every node waking up every epoch, okay? Which, again, we might not have needed data from all of them. Loss was not being modeled at all, including the loss of a whole aggregated wad of data. There were no quality guarantees in the system, and it was quite data inefficient in ignoring correlations both in space and in time. And this was shown to us very clearly. This is data gathered by TinyDB, so it's useful. I shouldn't say it's not useful. This is data from the Redwood Trees deployment, an early. It's from the lab? Oh, thank you. I think it's Redwood Trees. Really? All right, Carlos would know. So it's from the lab, and you can see the diurnal cycle of temperatures at the leaves of the lab versus at the you're spoiling my talk. The point being that there's clear temporal patterns when Carlos goes home, and I have to make this up on the fly now. Clear temporal patterns in the data, and also spatial correlations across sensors. The different lines are different sensors. And spatial and interattribute correlation is yet another thing I should point out. It turned out a good cheap way to acquire the light reading was to test the battery voltage, because they're highly correlated. Temperature, light, man, it's all about the ideas. You're all about the details. Whew. Did I mention these are Carlos' slides? So there's also interattribute correlation, and sometimes there's lower cost attributes. And in fact, Carlos and co, without me, I should point out, wrote a whole paper on which attributes to sample in what order for this sort of thing. So points to be taken. The data is not a uniform random sample. You shouldn't ignore the missing data because it's not as if it's just what you're getting is just a sample. Observing one sensor gives you information about other sensors on that node, on other nodes, and in the future, right? And observing what attribute gives you, as I just said that. Okay, so here's how BBQ works, and I'm going to have to speed up a little bit. Query would come in, and it would run into this big, fat probabilistic model, actually a very slim, little probabilistic model, which would be running on a PC. And that probabilistic model would have a guess at what the distribution of, say, temperature would be on a particular sensor. All right? It would have a multivariate distribution for all the sensors that you could ask about. And you'd give a query with some confidence. And let's say for the moment, the way that this would work is it would come up with a plan at the base station. And this is a source-routed plan. So this is very much in the spirit of what Deborah was talking about planning things outside the network. And I should point out to Deborah, she likes to do these little Berkeley UCLA things. She didn't appreciate sort of my Midwestern charming way of praising myself, which was to praise Chris for having such a wonderful idea that later in the day in my talk I would present it. So now I've shown my cards. Anyway, so data gathering plan, which is planned outside the network, it's source routed, is sent into the network, and a little tour is set up that runs around and just gathers data from those sensors that will help us answer the query properly. Okay, and once we get that data back, now all of our estimates in our model can be reconditioned based on the data we got back. And remember, because of correlations, we can condition attributes that we haven't seen the values for. Our confidence increases. So in this case, we don't have 100% confidence about the value of this thing. It's some correlated thing, and it's gotten much peakier than it used to be, and also higher. And then as time passes, there's a temporal model going on as well, where over time our confidence in that distribution is fading, and so we're spreading our belief wider in the domain. Okay? And the next query that comes in, well, gosh, maybe this time we can answer it off the model if this is within our confidence bounds for the query. Okay? And we don't go to the network at all. So some of the strengths here, you'll observe fewer attributes by exploiting correlations. You can reuse information between queries. And I should point out this isn't just caching, because caching doesn't really make sense in a dynamic setting like this. It's got to be something sort of predictive. You're directly dealing with the missing data by modeling it statistically. We're sort of answering more interesting queries. And then there's a very nice sort of graph theory meets networking problem of doing the selective data gathering with tours, which are source routed at the base, but in fact, in the network, they will run into failures and have to do things like little localized floods to jump back on the tour and so on. So we have a paper in Infocom on this problem that my student Alexandra Meliu has been working on algorithms to do this intelligent in-network tours. Okay, briefly, here's a problem with barbecue, though. So it's a wonderful system. I'm very proud of it. It would be really great if we actually got it working. But the simulation is really cool. I'll come back to that point. Here's a problem with it, which is this guy comes along, and he has a very localized phenomenon, which is he's making this thing really, really hot. That's right. It's a little very local barbecue. And the problem with BBQ is using its little nice model, a query will come in and say, what's the temperature like out there? It'll say, I think it's fine. The temperature's good. Everybody's happy. It's a sunny day. And it doesn't catch these sort of anomalous things happening in time and space. Okay, so what do you do about this? Obviously, you bring in your friend Ken to solve the problem, Barbie's little friend. So this was a different approach that was done, led by my student David Chu, working on this. And he's got a paper on this coming up in data engineering next spring. It's sort of a more push-oriented approach that's, again, using statistical models, but you can think of it this time as using them for compression rather than prediction, although it's kind of the same thing. And the way this is going to work is we're going to have a model, a little statistical model that's going to run at every node. And that same model is going to run at the base station. Exactly the same model. So think of it as being exactly the same code. And then what's going to happen essentially is if something weird goes on in the network, say these readings come in and they're way off where they should be on the curve. These guys know that the base station will mispredict the data. Okay? And so what they do is they say, hey, this is worth proactively routing towards the base station to recondition its models. And by the way, this guy in the middle can do some spatial correlation and detect that I don't need to route both of these up. I can just route one of these up, and this guy will be good enough that in the future we'll be able to keep everything together.
How much does that matter?
That's an interesting question I can't answer for you right now, but what I can tell you is that if that flamethrower had a slightly bigger scope, okay, then I just sent half the data by doing this instead of, it's one reading instead of two. How much does it matter to you? I don't know.
It just seems, this seems great, and this saves much more than just a factor of two.
The temporal modeling, right?
When this is really the main point.
We're smart. We try to do all the smart things we can think of. Maybe we don't need all of them. I'm not going to have a big fight with you about that. So the other thing that's nice about this, so you go ahead, you condition your new observations. You have to make sure these models are in sync. So these guys have to know if this guy played a game and didn't send up all the data. These guys have to know about that, so they redraw their curves to match his curve for the future, right? And all we're doing is statistical compression. It's actually not so different from like what text compression does. But from a user perspective, this is an alerting system. Suddenly, the network has proactively, without my asking for data, it has sent me an alert that something bad is happening, which barbecue wasn't able to do. All right, so the question is, we got all this cool stuff we've done, and right now it's all just kind of sitting out there independently. And there's all these other things that people have done that we're interested in, using gossip, algorithms for doing aggregation with gossip in a network. Carlos has done very interesting work with Sam Madden and others on using belief propagation algorithms inside the network, junction trees, to do localized pieces of a big model that's distributed in the network. There's the sorts of things that were mentioned this morning about leader-follower algorithms for tracking. There's ideas like Suman Nath has worked on for doing sketching techniques in the network. There's the distributed source coding work. There's all this stuff out there that's related to compression and statistics and modeling and things, and I don't know how this all goes together. There's also these details, details. What if your data is really big, like it's waveforms from Ralph's fab facilities at Intel? You have to ship those guys around. It's a very different ballgame. Wouldn't you like sometimes to get the data through for sure, and sometimes maybe not so much? And then another piece of the agenda that we really never got to in TinyDB is this automatic optimization. It's a declarative language. Usually the whole reason for having a declarative language is so that under the covers you can optimize. And we didn't do very much optimization yet. So we have that agenda remaining, and of course it's now been enriched by all the statistical issues we're dealing with. So what kind of query optimization opportunities are there for us? And these are all just for me big questions right now. So this is a fun agenda. And in the midst of this, we also have to keep Deborah happy and keep everything lean and just as simple as possible. Okay, so that's exactly what we're doing, of course, because we've anticipated her every desire and thought. We're starting very much bottom up. And what we said was, well, the first thing to do is to build a library of components that's reusable, unlike we did with TinyDB, and try to get a family of components that would allow us to prototype a lot of the ideas that have been in the literature. And we'll figure out how to put them together later into some unified whole. But we're going to start bottom up this time instead of top down. And so this is supposed to be like the standard template library, but instead of being, red-black trees, it's going to be things you would want to do to manage your data in a sensor net. And customers might be people who are algorithmic, like Carlos. His students don't really want to write TinyOS code. They would really like to specify communication patterns and make things go. People who are writing things like TinyDB, where they have a lot of tasks they're trying to accomplish. They're not interested in the details of each of them. System management tools are just data collection tools of various kinds, and they're being written onesie right now, still. So those are sort of the customers. And then the goals are we want to have a family of both communication tasks and communication patterns that support those tasks. So we've seen all these tasks. These are not magic. Dissemination of code or commands or something like that. Collection of data. Content-based multicast so that only the right people hear about something. And then there's various communication patterns to achieve various tasks. You can build trees. You can build DAGs if you want to do redundant transmission. You can do little tours like we've done, floods or local floods, gossip. There's this notion of Snoopy suppression. All these little tasks are things people talk about implementing, and they always re-implement them every time. And note that by separating these tasks and these communication patterns, we introduce yet another opportunity for optimization. If all you care about is the data gets disseminated, maybe I can be clever about choosing which of these things to do, okay, under the covers, and you don't have to think about it. So that's a goal of this, even at this lowest level, is to separate out this sort of coarse who is saying what to whom from how it's being done. Okay? The tiny schema stuff from TinyDB was good to have a collection of high-level attributes that you can talk about instead of thinking about devices and little pieces of code is nice. To have a range of transport options, so we're working very hard to make sure we can now do large object transport with varying reliability as well as small objects, and being able to choose, how hard do you want to get the data point to point or end to end. And then have a flexible use of the memory hierarchy. This is particularly important for large objects. If you're transferring something that's many, many packets big, where will it reside during transit at the various stages? Is it actually going to stay with the sensor, so to speak, and stream out in real time, packet by packet? Or is it going to be buffered in RAM or perhaps in Flash? Or how are you going to manage the network? So we're trying to allow that to all be pluggable to suit. And so that's kind of the SD-lib agenda. And just right on time, I'm on my last slide. So having talked about all that stuff, I have a pal, Danny Malman at the U.S. Geological Survey, who's interested in using sensor nets. And he spent about a year canvassing people at the USGS about, what would you do if I gave you this stuff? And oh, by the way, I only have 1 year of funding at the USGS, so I'd like to figure this out quick, so you'll fund me. So he's motivated, which you always like. And after talking to lots of people, the first order thing that he thinks we can actually make a difference on, or I think we can make a difference on, and he thinks is important, is what's called debris flow. And this is what typically happens after a wildfire. Okay, it happens in California a fair bit. Wildfire happens, plants are taken away, ground cover is taken away, and you get landslides. Okay. A nice thing about debris flow is that there are these things called watersheds, which is just basically the topography in any region. Some watersheds are like the Mississippi Valley. Okay, some of them are gigantic, but if you're in a hilly area like California that tends to be very small, it's the downslopes to some exit point into the ocean typically. Okay, so a watershed is a place where everything is flowing in one particular direction, and you kind of know where things are going to go, which from a sensor net perspective we thought was attractive because it makes the tracking problem easier. You kind of know roughly where things are going to go, and in fact you can sort of set up your communication and as well as your deployment to be a wireless watershed where the data is going to flow the same way as the phenomenon. Right? It's a nice constrained kind of playpen for computer science as well as for geology. So he's going to get us a half-mile square identified watershed. USGS is doing one this year, one next year. It's burned recently. It's probably going to move this year. They want to start getting equipment out there. And they already have things like a big truck with Doppler radar that can do lots and lots of weather gathering, but they don't have any microsensors of any sort. They have water levels and things. So I have 2 little videos of debris flows just to whet your appetite. The first one I know a lot about. The second one I actually couldn't get a hold of Danny to find out what it is, but it's really cool looking. So this is a street in a little town in California that a guy videotaped out his front door. It's in Devore, California. And this is on the USGS website. So you're seeing, debris flow outside his house. And the thing I think that's most striking about this that Danny pointed out to me is the water in this picture is actually of the consistency of poured concrete because it's got so much sediment in it. So these guys, these geologists who spend all day, they're so excited about sediment transport. It sounds so boring, but imagine being stuck in a flowing stream of concrete with big boulders. This is another one where I don't know where this is and why it's so sunny while this is happening, but this is another video. This is a debris flow. I assume it's real and not like some USGS hoax, where in 54 minutes it's carved that path, the landslide. So it's pretty exciting stuff, but it has this property. You kind of know where it's going to go, and what they're really interested in is what are the initial conditions that start the soil moving. The geologists don't understand those dynamics at any micro level, so there's an interesting science problem. And they're also committed to building early warning systems for these things. So they're also interested in when things start to move, they want to get, triggering downstream as quickly as possible. So it's kind of a fun playpen. It's kind of an interesting and useful playpen for us. I like the constraints on it.
Any questions? Got it,
So this is very interesting. And what's nice is that I think your first version of the problem, which is about trying to understand the conditions that cause that transition, seems very much in need of the dense sensing. And then the tracking stuff I would do with remote sensing.
Well, certainly this one you could see from up in the sky. That was good.
Mm-hmm.
Yeah.
But in any case, it's always interesting to think about that.
Where the trade-offs are.
What's the right tool?
Yeah. And I've been talking with Leo and Carlos actually about a mixture of cameras in this environment with this stuff. Okay.
Okay, questions? Other questions?